Okay, so we are talking about Dijkstra's algorithm. So we want to work out the Dijkstra's algorithm on this given input. So just to recap, in a Dijkstra's algorithm, what we are doing, we are starting with a vertex S, that is also a part of the input. Suppose this is the graph, and suppose A is our S. Okay, so this is our S, say, starting vertex. This is also part of the input. So the input will be a vertex which we have to be. This is a single source shortest path problem. So given a vertex S, we have to find out the shortest path from all other vertices. Okay. So basically, what we are doing, we are just maintaining the this thing. We are putting everything in the queue. So our queue is basically A, B, C, D, E. Okay. So we are putting everything into the queue, and we are putting the degree of this as this. This is the initialization step of this Dijkstra's algorithm, if you recall. So we are just putting the degree of S as 0, and for all other vertices V minus S, we are putting degree to be infinity, because this is the initialization this step, nothing has explored, and S is this Q is the basically all the vertices. So we are putting all the S is empty, capital S is empty initially, and we are putting all other vertices in Q, which is the priority queue. Okay. So basically the idea is we just capture one each time, we just capture one vertex in S, and we will update the distance estimate of that vertex which are adjacent to that vertex which we have recently captured. Okay. So now what we do, we do the extract minimum. So we do the extract minimum, U is the vertex. So extract minimum from the Q. Now initial, so everything is infinity except this. So this will be the this will be our U. Okay. And this once we extract minimum, we'll put it in S. So S will be S union U. So S will be A, because it was empty. So this is our U. Now once we have U, then so we look at all the vertices which are adjacent to U. So this is one vertex which is adjacent to U. So this is V vertex. So we look, so all the degree was infinity. So we look at the vertex which are adjacent to U. Now its degree was infinity. Now we have du is basically 0. So 0 plus this w u comma v, which is 10. So that is basically 0 plus 10 is 10. So 10 is better than infinity. So we have to decrease the key, we have to change the degree. So this become 10 now. This became 10 now. Similarly, now this is V, which is another adjacency vertex of U. Now it was having a degree infinity. Now we have a path, we can go from S to S with the cost 0, then we can take 3. So this degree will be now. So this is the relaxation we are doing, we are relaxing the vertex. So if we do this relaxation, the C became now 3, and then so there are only 2 adjacency vertex of this, and these 2 will be copied, no change over here. Okay. So we can just this one copy this one. Okay. So now this is the first round. Then again we have to check whether Q is empty. Q is not empty, still they are in the Q. So Q means V minus A, S, capital S. So they are in the Q. So these 2 are infinity, and this is, so now we have to extract minimum again. So now if we extract minimum, so then this 3 is the minimum, because down all are 10, 3, infinity, infinity, 3 is the minimum. So this is our U now. So U is basically extract minimum from the Q. Okay, now this 3 is the minimum. So now this u is now added. So u is basically C. So C is added in S. Okay, so C is added in S. So now this is our u. Now we check all the adjacency vertex of this. So this is one of the adjacency vertex. This is V. Now this is having a degree infinity. Now we have a path from S to this node. How? So this is basically du is basically 3. So that is same as delta of S comma V. So that means once a vertex in is S, once we are capturing its vertex. So once u in S, so that means du is basically delta of S comma u. So this is the correctness of this theorem, Dijkstra's theorem. So once we capture a vertex in S, then and this correctness is coming from triangular inequality. Okay, so once we capture a vertex in S, capital S, for that vertex the delta of degree is basically becoming the shortest path from S to that vertex. Okay, so now this is 3. So now from S to V, what we can do? We can go from S to U with a cos 3. Then we can take this direct path. So 3 plus 2 5, which is better than infinity. So we change this to 5. So E is now became 5. Okay. Now it is another. This is also V. So it was infinity. Now we have 3 plus 8 11. So this is 11. So D is 11, and now this is another vertex which is adjacent to this. Now this is our V. Now it was having a degree 10. So that means there was a path from S to this vertex with a cos 10. Now we have a new path from S to this vertex. How? We can go from S to U with a cos 3. Then we can take this direct path 4. So 3 plus 4 7. So now 7 is better than 3. So this path is better. So we must relax this h. So we must relax this h. So this will be the now 7. So this 10 now became 7. Okay, and so this there is no other adjacency vertex of u. So we do what? Now we will extract the next minimum. Next minimum is 5. So 5 is basically this one. So this is our u now. So we capture this in S. So now this is our u. Now what is the V? V is this one. So there is only one adjacency vertex of this. This is V. So what was the degree of V? Degree of V was 11. So that means there was a path. There is a path from S to V with a cost 11. Now we have a new path. What is that path? So we can go from S to U, and this cost is basically du, which is basically 5, because this has been added in S recently. So that means the degree is becoming the delta for this vertex. So this is du, and then we can take a direct path, that is basically 9. So this cost is 14. So we come from S to this with this shortest path. Then we take this direct edge, which is 9. So 5 plus 9 14, which is not good as 11. So we will not relax this vertex, because the earlier path is better than the path currently now we are having. So we are not going to relax that vertex. Okay, so this will remain 11. So this is the situation. So this will be the infinity, and this will remain 11, and this will remain 7. Okay, now we extract the next minimum. Next minimum is 7. So this is our u. So this is 7, and this B will be captured in S. Okay, so now this is our u, which is 7. So now delta of u is basically 7, which is basically d of u is 7, delta of S comma u. So that means from S we have a path and that is the shortest path. We have a path from S to U with a cost 7. So, that path is basically shortest path because this U is recently captured in S. So, whatever the vertex we are taking in S, for that degree will become the shortest path weight from S to that vertex. Okay. So, now let us consider all the adjacency vertices of this node. So, this is one adjacency vertex. So, this is now V. So, if this is V, then the degree of V was 11. Now, we have a new path. We can go from S to U some way, and that path is basically 7 cost. Then we can take this direct path 9, and that is better than 11. So, new path is better than 11. So, we have to relax this edge. To relax this edge, so we have to change this to 7. Sorry, 9. 7 plus 2, 9. So, this 11 now became 9. And is there any other adjacency vertex of this? Yes, this is one adjacency vertex of this, but this is already captured in S, but again we can cross verify, because we are getting another path from, this is also a V which is adjacency vertex of this. Now, we are getting another path from S to V, like we go to S to U some way, that will cost us 7 plus this 1. So, 8. So, but we already have a path which costs 3, which is not better than the 8 is not better than 3. So, that is a cross verify that it is working fine. Okay. So, this is that is it. So, this is the two vertices which are adjacent to this. Then we again call this extract mean, and this is the vertex which are going to be add in D. Yes. So, that is it. So, this is the and this Q is empty now, because all the vertices are now deleted from this Q, priority Q, and has been captured in S. So, now these are basically deltas. So, delta of this box are basically giving us the delta. So, delta of S is basically A, delta of A comma A is 0, delta of A comma B is basically 7, delta of A comma C is basically 3, delta of A comma D is basically 9, and delta of A comma E is basically 5. So, these are basically degree of those vertices. So, this is the Dijkstra's algorithm execution. So, here we are assuming no negative cycle. We cannot, Dijkstra's cannot handle the negative cycle. So, that is why we strictly follow there will be no negative weight H in order to avoid the negative cycle. Okay. So, just let us go for a quick correctness of this theorem. So, the idea is we just grow this capital S, we capture each step, we capture one vertex in capital S whose distance estimate is minimum. So, distance estimate from small s to that vertex is minimum, and that is the greedy choice. So, that is why this algorithm is a greedy algorithm. Okay. So, correctness is basically telling us there is a two theorem for this correctness. So, it is telling us so we can just write in one theorem. Yeah. So, Dijkstra's algorithm terminates. So, when we finish this execution, then with dV is equal to delta of S comma V for all V. So that is what we are expecting, because when we capture a vertex in S, so how to prove? We will just give the outline of this proof. Okay, so basically what? Basically when we execute, when we finish this algorithm, when we finish the execution of this algorithm, then the degree is becoming the this. So to prove this, we can just prove this. So if you recall the Dijkstra's algorithm, what we are doing? We are maintaining a set S. So first of all, we are initializing each degree by, so we are initializing degree of S is 0 and degree of all other vertex. This is the initialization step. All the vertex from V comma S, we put the degree to be infinity. Okay. And now in the first step, the S, capital S is becoming, we are just capturing the smallest in capital S, because, so now small s, this degree is 0. So now what is the delta of S comma S? Delta of S comma S is 0. Why? Because there is no negative cycle. So that means from S to S, what is the best way we can go from S to S? If you remain at S, because there is no other way. If you start from S, there is no other way, we can come back to S with less than 0, because there is no negative cycle. If there is a negative cycle, then there could be a chance that we can have this hop in this path, and then we can just do that. Okay, since there is no negative cycle, so that means there will be no question of reducing this to further 0. So that means this S will be in S and the degree of this is 0. So for S we are fine. So d of delta of S comma S is basically 0. Okay. So now now what we are doing? We are doing here. So we have a S set, capital S, which is small s should be there. Now we have a set V minus S. Now there are some vertices over here. Okay. So now among these vertices, so these are the degree of these vertices. So say this is say U1, U2, suppose UK. I mean there are say okay. So now degree of now here what we are doing, once we capture a vertex in U, then we take a V over here, which is basically, so this is basically delta of, so what is the degree of V? So degree of V is basically degree of U plus delta of U comma V. So initially this is S, basically U is S. Okay. So now if we choose the minimum among these, so this will be become, so this is basically, if you take S to this vertex, any other path, so that is basically any other path from S to that vertex, that will be the less than that. So my claim is delta of V must be greater than equal to d of V must be greater than equal to delta of S comma V. So how to prove this? So to prove this, what we do, so this is the shortest path from S to V. Now this is one path from S to U, then U to this. So this is the weight of that path. Now, so delta must be less than equal to that. So that is the triangular inequality we are using. If you remember, the triangular inequality is, if we have two vertex UV and if we have another vertex X, then if we have a shortest path from S to this, so this is basically delta of u comma v and delta of u comma x, and this is basically delta of x comma v. Now this is basically s, u is basically s. Now this is basically say s, u is initially this u is s, because initially we are capturing s in that set. Okay. So now this is basically the shortest path from s to s, because this is degree which is 0, and this is basically the direct edge from s to that vertex, or any so sorry, we are not talking about s. Anyway, let us take any other vertex. So this, suppose this is true for, we can use by induction. Suppose this is true for up to k. Now in the k plus 1 step, we are capturing one node, and we have to prove that is true for k plus 1 step. So if we assume this is true for up to k step, so that is the degree. So this is basically delta of s comma u, because this is the assumption we are making. So this is basically delta of, sorry, this is du now. Okay, this is du. So delta of s comma u by the induction hypothesis, and this is the direct path. So this is the shortest path from u to v. Okay. So now, so this is basically must be this must be less than the shortest path. The shortest path must be less than this. Now if this happen to be the minimum which we already have, this has to be there. So that is by the, because this is the delta of u comma v. So this is delta of s comma s, then this is, so this means this must be greater than equal to delta of s comma v. So this is coming from this triangular inequality. So when this is true, if the s is in, if the v is in capital S, then the equality will occur. Anyway, so this is the correctness of this theorem, and this is coming from the triangular inequality. And so we have already seen the time complexity for Dijkstra's algorithm, which is basically same as Prim's algorithm. So the analysis part of Dijkstra's is same as Prim's algorithm. So now we will talk about the another algorithm which is basically can handle the negative weight cycle. So which is called Bellman-Ford algorithm. So before going to the Bellman-Ford algorithm, let us recap the problem with the negative weight cycle. So far we have seen the Dijkstra's algorithm. But in Dijkstra's algorithm, what we have, so this is a single source shortest path problem. Single source shortest path. So that means we have given a input is a graph with a vertex as a source, a graph, directed graph. A directed graph G, V comma E, and a vertex which is source vertex, and the output will be the this output will be the delta of s comma v for all v belongs to capital V, and also we have the weight function e to r plus. So here we are not allowing the negative weight h, because Dijkstra's cannot handle the negative cycle. So no negative cycle. So we have to guarantee that in order to run the Dijkstra's algorithm, we have to guarantee that there is no negative cycle. To guarantee that, we are taking, to be safe side, we are taking no negative weight h. Okay. So that will ensure that there will be no negative cycle. So what is the problem with negative cycle? If we have a negative cycle, then although if there is a shortest path, if there is a path from u to v, there may not have a shortest path. If we have vertex u to v, so this is v0, v1, v2, say vl, vk, and if there is a negative cycle over here, okay, which will not the case in Dijkstra's algorithm because there is no negative weight edge, but in general we can have a negative weight edge. So, that may create a negative cycle. So, if there is a negative cycle, then there will be no shortest path. So, in that case delta of s comma v will be infinity, because if we cannot claim that there is a shortest path, because if we claim this is a shortest path, then we will have another loop in this cycle. So, this will reduce further. So, this way we can keep on reducing further. So, this way we cannot have a shortest path form. So, we will not having a shortest path form u to v if there is a negative weight cycle. So, the algorithm which we will discuss in the next class is called Bellman-Ford algorithm, and that Bellman-Ford algorithm can handle the negative weight cycle. So, so for Bellman-Ford algorithm, our graph is any graph with the any edge weight. So, we are allowing the negative weight edge also. So, there will be chances of negative cycle. So, Bellman-Ford can detect the negative cycle. If there is a negative cycle, there will be no shortest path, but Dijkstra cannot say that there is no shortest path, since there is negative cycle. Dijkstra cannot say that, because Dijkstra cannot handle the negative cycle. So, that is why we take the assumption the weights are positive. So, in order to avoid the negative cycle, but in Bellman-Ford it is a general algorithm. So, it is more general than Dijkstra. So, there we are allowing the negative weight h. So, there could be a negative cycle. So, Bellman-Ford should able to tell us that okay, there is no shortest path because of negative cycle. Anyway, we will discuss this Bellman-Ford algorithm in the next class. Thank you.